going to be symplectic. And when M is odd, then the singularized structure is going to be this, the singularized structure. What it does is to take something which is non-smooth as the RAM differential form and transform it into a smooth differential form. Of course, this transformation is not miraculous. What you do is to change. You have your manifold, you have a differential form, and what you do is to take a new differential form. Okay? So at the end of the class today, what I will see is that when M is even, if a manifold admits such a structure, it also admits a symplectic structure. This means that all the obstruction theory that applies for symplectic theory applies for even dimension, for even exponent. And when M is odd, this becomes as a folded symplectic manifold. Folded symplectic manifold, this word appeared in my first class, and this means that omega is of this type. I can write this as a differential form of this type plus higher order terms. I also need to be dealing with even dimensional manifolds. This is the same. And observe that in this case, I'm very tempted to look at this as the differential of x1 squared. Okay, and this is why this is called fold, because this is like the image of this is that it has a fold. Okay, and this structure, what happens with this structure? This structure now it's a smooth. Okay, if you want to think of it as a dual to this structure when m equal to 1, but this one is a smooth, but it doesn't have the maximal rank. Let's say it has the property that omega n is not a volume form, but it's almost a volume form. You can write it like that. When I have this, I can say that this differential form is transverse to the zero section. Transversality, I measure it in the sense that the function x equal x1 is a regular function. Okay. And I also need to require that the restriction to x equal to 1 is of maximal rank. When I have this, I have a folded symplectic form. That's what it's called folded. This will come at the end of my talk. So then in perspective, we will be able to put, to understand, related to the list of exercises, the obstructions for a manifold to admit a B symplectic form or a B2 symplectic form in terms of another geometrical structure, which is the symplectic structure of folded symplectic. Okay. An interesting thing about these systems is that they have an induced dynamics. So x1 equal to 0 in these models obviously is the problematic locus, and this locus we will call it the critical set. And then what's very interesting, and this is what I want to put by this picture of a man walking on a wire, the idea is that you have an induced dynamics and induced geometry on the critical set. And today I also plan to explain this. This is what I plan to explain today. So we don't have this kind of billiard situation because the dynamics restricts to the critical hyperspace. Okay. Oh, sorry. Now let me go to the next one. Sorry. I have now I'm moving. Okay. Moving like this. Remember that I said that the image that you need to have to understand like a first model, and this was the question of Chung, what does it mean to be controlled as a first example, and this would be an example of B symplectic or B Poisson. So B symplectic or B Poisson is the same, but the way we express this structure, if I use a differential form, I'm going to call this B symplectic. And this would be the B symplectic form. But associated to this, I can dualize, and I can take the Poisson structure defined by this, like the dual Poisson structure, okay? And this is something that you cannot always do. So if you have a differential form, you cannot, like, this is not always possible, but you can do this if you are even dimensional. You can invert this matrix, and then what you get is something that it's a smooth. This is a bivector field. So there is a whole world which deals with bivector fields, which you can think of them. What is a bivector field? It's a more complicated structure than a vector field, okay? But you can think of it, I think it's very easy to think it, in terms of that it's dual to a differential form, okay? Then you have this bivector field. And when you have a bivector field, sometimes you are lucky and you have a Poisson structure, okay? When does this happen? For this, you need to have a condition that in terms of bivector fields, we write it like this, but this is equivalent to a Jacobi condition that I will explain in 2 slides, okay? And for that, I need to associate, to talk about the Jacobi identity, I need to be able, when I have a bivector field, like this one, to associate a Poisson bracket. How do I do this? I can associate a bracket of functions. In this particular case, I will do this later, more general, but just as in terms of example, if I have a couple of functions on the surface, okay, then I just define as a differential form, as a bracket. I can pair, this is something that was in one of the slides yesterday. I can pair this bivector field with the differential of f and the differential of g. And this defines an assignment that it's a bracket because it takes 2 differential functions and gives me a differential function. And that's a bracket that it's a Poisson bracket. This is an assignment. And I say it's Poisson bracket if it satisfies 3 conditions that I'm going to see. I'm going to write this in slides, but are very simple. Antisymmetric, Leibniz rule, and Jacobi identity. If I already have a bivector field, I don't need to check the 2 first conditions, because in order to be able to write something as a bivector field, it has to be antisymmetric and it has to satisfy already the condition of Leibniz, okay? The problematic condition is the Jacobi identity for this bracket. And the Jacobi identity for this bracket is going to be equivalent to this condition in terms of bivector fields. What is this bracket? This bracket is called the Schouten bracket. And I can just understand the Schouten bracket as a generalization of the Lie bracket to bivector fields. So if I just know how to apply the Lie bracket to vector fields, I know how to apply it to Schouten bracket just by thinking that it has to be compatible with the wedge. And I mean, this course is not about bivector fields. I just plan to walk over Poisson manifolds without getting burned and already get into differential forms. And essentially the language we will be using is that of differential forms. Why differential forms is more convenient? Because, for instance, we can try to copy the path method that I explained the other day. That's a good reason. Okay, but what it's true is that at the beginning, when we started to work with these structures, with Victor Guillemin, we were one day sitting in the sun of Lausanne. It was, of course, summer, otherwise you don't have sun in Lausanne. And we were playing like, how can we do something in Poisson geometry that it's very simple? And then we realized that nobody had studied these structures for general manifolds. These structures were studied in the case of surfaces by Olga Radko, who is here in the picture. And indeed, that was her PhD thesis. Her PhD thesis was to completely understand the Poisson geometry of a surface that has this kind of singularities. Okay, this kind of singularities here I call controlled. I'm going to give a proper definition. And controlled is going to be equivalent to transversality in geometry. Okay, so The geometries involved, again, where are we? We are here, somewhere between symplectic and Poisson, but we could try to go in many directions. As Raju was asking on Tuesday, we could try to go to generalized complex. We could try, as he was suggested, to work out this V generalized complex. This was a very interesting question. And as I say, today we have to zoom in and zoom out. So sometimes, sometimes it's convenient in life, okay, if you want to look at the details of a picture, we need to zoom in. But sometimes when you zoom in too much, like is this picture, maybe you don't recognize that you have a flower and you lose the beauty of the flower. So sometimes it's good to zoom in, but sometimes it's good to zoom out to see this flower as a part of a garden. And today we're going to be zooming in and out to gain perspective, right? And to zoom out will be equivalent to look at these structures as a Poisson structure. And to zoom in will be to think of these structures as a symplectic form, which is not a symplectic form, okay? But something that behaves like a symplectic form. And the conclusion of the day is that it's interesting to study both points of view, okay? Let me talk about Poisson. Who was Poisson? Poisson in long time ago, he gave this formula in his Mémoire sur la variation des constantes arbitraires sur les questions de la mécanique. He gave this formula here that I'm highlighting, and this formula here, it's written in a very strange way. But this bracket here that he puts as VA wants to be the Poisson bracket of the functions VA. And this defines the Poisson bracket, what we call the standard Poisson bracket. What is the standard Poisson bracket? Well, the standard Poisson bracket is the one you associate to symplectic geometry. Okay, if you have a symplectic structure, you can define a Poisson bracket in the following way. You take omega, okay, the symplectic form, and you apply it. Omega is a two form. So the two forms can need two differential forms. So this omega will lead the differential of F and will lead the differential of G. Okay. What is this? This is a two form applied. Sorry, I said something. I'm sorry. There is an error here. Sorry, I wrote, I was thinking in the Poisson thing. Wait, let me erase this. Where is now? I lost control of my tablet. I want to write.
Just click on the pen up there. Now it's back.
Where is back? Do you see it?
If you click on the pen up there on the top right, then it appears on the bottom left.
Yeah, this is what it should happen, but it has disappeared. Do you see it?
No, we see it actually. When you click up there, we can see it in the streaming.
Oh my God, I'm the only one who doesn't see it.
Now it's gone again. So
it's gone. I do this. Okay, here. Thanks a lot, Marcello. I'm very happy that you are here. Okay, I made an error here. I said Hamiltonian vector fields. I mean, it doesn't make sense, okay? I said a differential form, it's a vector field, and I put a form. It doesn't make any sense. This is the Hamiltonian vector field of F and the Hamiltonian vector field of G. Let me remind you, I gave the definition the other day. What is the Hamiltonian vector field? Remember that is the unique solution to this equation. Okay, so that's the definition I'm applying. And I say, when you have a symplectic manifold, this defines, I mean, by the way, guys, Pau and Joachim, this exercise should be in the list. Pau, we have to add this to the list, okay? Because it's not in the list. I think that's yeah, I mean, that was in one of the former list of the, that's a very nice exercise. So it's an exercise in the list to check that this has this satisfies the condition of Poisson bracket. The condition of Poisson bracket is here. Okay, a Poisson bracket is an NER bilinear operation. Okay, so an assignment given two vector fields, two functions, I define the bracket, and this gives me another function. And we need to check that it's anti-symmetric, that satisfies Leibniz rule. Leibniz rule, indeed, it means that the assignment, so remember, in the symplectic case, so what we call the standard one, standard bracket, satisfies omega xf xg. Okay, and this is a function because I'm pairing a differential form with two brackets. You can write this in many ways because you could do this as the contraction of xf, okay, with omega applied to xg, and you can play with these equations, and it's interesting to play because you can even recover Noether's theorem, and then you can see that this is x sub the Hamiltonian vector field applied to minus the differential of f, for instance. Okay, that's a way you can think of this in this term. So it's the Lie derivative of the vector field x sub g. So if by this equation we realize that when I fix f and I leave g free, this acts as a derivation. And the same when I leave f free, okay, and I fix g. This proves this, okay, but of course omega is anti-symmetric, therefore this is exactly the same as x sub f differential of, with a minus is anti-symmetric, so I have a minus that I'm eating. This is the same as the differential of g. So by these equations here, I'm already proving that in the symplectic case, this satisfies the Leibniz rule, because the Leibniz rule indeed is equivalent to say that when I fix one of the functions, this is a derivation. So the Leibniz rule tells you that this is a biderivation. And the first condition, anti-symmetry, this is satisfied here. And this is indeed equivalent to the fact that if I have a function with itself, this is equal to 0, and you can interpret this as the Noether's theorem. And that's an interesting thing that it's in the notes. In the notes that you already have, this is explained, by the way. But I think it's good to explain this in the class of next Thursday, in the class of problems. Okay, this is equivalent to this anti-symmetry here that I am proving with these funny equations in the symplectic case. And Jacobi identity, why Jacobi identity is satisfied? That's maybe the only point to be checked. Okay, Joachim, and this is something that I think it's worthwhile to include this. So let's say this is the Poisson bracket that Poisson introduced. But look, Poisson introduced this bracket associated to a symplectic manifold. The first message I want to throw is that this is a first step, but there are many other situations in which you can define the bracket. Okay, in the former slide here, indeed, I was explaining in more generality what I already wrote, that if you have a bivector field, for instance, to be able to write, and this requires some thought, but to be able to write this bracket as a bivector field, you need that conditions 1 and 2 are satisfied. So if you have a bivector field, okay, if you already have a bivector field, it means, so if the Poisson structure is given by pi, this already means that 1 and 2 are satisfied. The fact of writing the bracket this way is already telling you that these two first conditions, anti-symmetry and Leibniz rule, are automatically satisfied. Why? Well, think of the following. Remember when you were undergraduates, they were telling you, okay, that it's the same to give a Lie derivative than to give a derivation. And a Lie derivative is the same as a vector field. Now I have a bivector field. So this is equivalent as having two derivations. So this is equivalent as being able to write the Leibniz rule. Also, antisymmetry comes for free because it's impossible that you write a Poisson structure as something that is antisymmetric if you don't buy that it's antisymmetric. You agree with me? So that's the formula that gives you that if you have a bivector field, how can you go from the bracket to the bivector field? And that's the formula that you can use. There are some examples in the list that are very interesting how to do this. And I think it's worthwhile because, of course, if this was a master course, then I would be like today explaining Poisson manifolds and so on. I will explain something about Poisson manifold, but I need to go on and talk about our particular class of Poisson manifolds. There is a whole world behind the world of Poisson, which is very interesting. Of course, a first example of Poisson bracket is the one of symplectic forms. But now I'm going to ask the public to give me another example. Let me see if I can see your faces. I cannot. So I'm going to ask, can I see your faces when I'm doing this? Yes, I can. What I cannot see is the, okay. Do we have any volunteer to give me another example of Poisson that is not the B Poisson or symplectic? I could ask this to Joachim and Pau, but or Anastasia, but I know they know this. So this would be like theater. This would be like prepared. So any volunteer? Raju, do you have any suggestion? For instance, I'm going to give you an example, and I want to convince you that this is true. Like example, and I could say that this is like a silly example, but it's totally valid. Okay, to have a silly example sometimes, which is now imagine that I take a manifold. Which manifold? I don't care. Take your favorite manifold. What is your favorite manifold? For instance, Pau, who can speak. Pau, what is your favorite manifold?
Well, I can.
Don't tell me it's the Euclidean space. I would be disappointed.
No, I can think. Yeah, for instance, a torus or a sum of tori.
Okay, you like torus. Okay.
P2.
Of which dimension?
Any
dimension.
For instance, 4 or 6.
You like torus of dimension 4. Okay, I will not judge you. This is good. And somebody else, maybe, Marcello is also voting for a torus. How do you do this to put the torus there? That's nice. Okay, so Marcello also has the torus as favorite one. So we have 2 people in the class who like tori. Okay, that's good. I mean, I don't know. I thought that, I mean, if I asked Joachim, he looks like he likes non-orientable things. No? What about this? You look like a non-orientable guy. Take whatever. Take a Klein bottle. Klein bottle. Why not? This is non-orientable. Okay, we are here doing a dangerous thing, taking non-orientable manifolds. And now I tell you, if I take the torus like Marcello Pau like or the Klein bottle, okay, what I do is to define the following structure. I take the infinite functions. These are smooth manifolds, M1 or M2, it doesn't matter. And I'm going to define a bracket. And the bracket I define is I send any couple of functions to the 0 function. You are going to think that this is something that should be forbidden. Okay, it's impossible. How can you send everything to 0? Why not? I send everything to 0. Okay, in terms of bivector fields, this is a 0. This means that the coefficients in any coordinate system are 0. And in any possible, if I write this in coordinates, everything is 0. Is this legal? Yeah, this is legal. Let me check that it satisfies. First condition, yes, 0 equal to minus 0. Second condition, 0 equal to 0 plus 0. Third condition, 0 plus 0 plus 0 equals to 0. So it's okay. So any manifold can be a Poisson manifold. That's the conclusion. Any manifold admits a Poisson structure. That's indeed very refreshing, right? Because if I give you a 4-dimensional sphere,
but if I invert this, then the symplectic structure will have a singularity, right? Due to this.
Yeah, well, I mean, this is a very, yeah, Raju, this is absolutely right. There is no symplectic structure. So Raju is saying an interesting word here. He's saying symplectic. This is not symplectic. So what I'm saying is that here, if I have a symplectic manifold, I can define a bracket, but I can also define a bracket if I don't have a symplectic structure. That's the news, okay? But Raju is trying to relate, and I think this is something very good. He's trying to relate this example with the former example. There's something true about what Raju is saying. If you have a Poisson manifold, there is a way to decompose the manifold as a union of symplectic manifolds. That's true. That's a fact. That's something I'm going to prove. And Raju has put this idea now on the table. So let me explain you that in the case when I take this very degenerate Poisson structure, 0, okay? 0 is the number that you don't want to see as a result of your exam, right? Is the forbidden number. But if you get this 0, this means that these symplectic manifolds are just points. So they are very degenerate, as Raju is observing. We can associate symplectic manifolds to this example, but they are points. Maybe we don't like points. If I ask what is your favorite manifold and you tell me that it's a point, I will tell you, okay, this is not, why are you doing this mini course, right? A point is not very exciting, okay? Let me ask you something, like what about a sphere? Okay, spheres have something magical. Let me ask you, a sphere, dimension 2 has a symplectic structure. Yes, the area 4, you told me. Any orientable surface is symplectic. And well, here I left a space for proofs. This is good. Okay, otherwise I'm going to be. So now I'm going to ask a question for the general public.
So it should be like R dr wedge d theta. R dr wedge
exactly.
d.
So if I take, so for S2, okay, exactly. For S2, maybe the best way to take is to take what physicists call a Immutal Angle, that I like so much, this expression, which means that I take as coordinates, well, the angle. So I take H and theta, and then I take as a form the H wedge theta. If I change to cylindrical coordinates, I get what Raju is mentioning. Okay, this is on S2, this is a symplectic structure. Now I'm playing games and I'm tempted to ask you, this is solved already in the notes. What about S4? Since Paul liked 4-dimensional tori, okay, I like 4-dimensional spheres. But I have a problem because I like symplectic geometry. And the truth is that S4 cannot admit any symplectic structure. How do I know this? Something magic happens. Somebody wants to say something. Marcelo, who is talking? Paul wants to say something?
No, I mean, you said why this cannot be symplectic, and I just remarked maybe by using Stokes and the boundary is empty.
Exactly, using a Stokes, indeed, this is done, and I'm very glad. If you look at the first page of the notes, you find the proof of the following proposition by using a Stokes that very simply that if you have a compact symplectic manifold, the symplectic form cannot be exact. A symplectic form on a compact manifold cannot be exact. Be exact means that this 2 form is the differential of a poor 1 form. Of course, omega is closed because this is the definition. This means that I can take the class of omega because this defines a cocycle in H2. Okay. So what this means is that this guy cannot be 0. What happens if you have a manifold? So this means that your symplectic structure defines a non-vanishing class in H2. So what happens if you have S4? If you have S4, you take S4 to your favorite doctor and he will tell you that H2 is 0. Okay, I take the S4 to an algebraic topology and the algebraic topology tells me that, of course, this sphere has H2 equal to 0. Indeed, any sphere which is not S2 has this problem. So this means that, unfortunately, my favorite manifold cannot be symplectic. Okay, so S4 symplectic, no, S4 cannot admit any symplectic structure. There is a problem in the list that it's very interesting. Can it admit a bisymplectic structure? I still didn't define, but this is connected to this proof. Okay, and you can solve this by trying to reproduce this proof, or you can solve this by using problem. This is problem 1.6, and you can use problem 1.7. So that's the space for proofs. It's very convenient that I thought that I needed a space for proofs. And in this other space for proofs, I'm going to talk, this was like a general question, but I'm going to address what Raju suggested. What is the relation between symplectic manifolds and Poisson manifolds? Okay, well, we have understood that any symplectic manifold is Poisson, but not any Poisson manifold is symplectic. Okay, we saw it with this trivial example. So if I have to put things on a line, I would write here symplectic. Indeed, this is the Poisson line. Okay, so this is the Poisson line, and in the Poisson line, symplectic would be the first example of Poisson structure. Let's see. Well, I also have the 0 structure here. Okay, but symplectic would be an important class. I want now to relate symplectic to Poisson, and this is what I'm going to do. I'm going to first say it with words. A Poisson manifold is a union of symplectic, is a union of symplectic manifolds. That's the relation. And not only that, but the structure, the Poisson structure restricted to the symplectic manifolds is exactly the one defined by Poisson in 1809. It's the same, it's the standard Poisson structure. Okay, that's to say it with words. I can think as a Poisson manifold as a decomposition of my manifold, and this union is not finite in general, a decomposition of my manifold into different submanifolds that are symplectic. How do I get this decomposition? Okay, and now I'm going to play a very interesting game, which is first, I'm going to extend the definition of Hamiltonian vector field. This already is in the notes that are online. If I have a Poisson structure, and I'm going to use here the language of my vector fields just for convenience, if I want to define a Hamiltonian vector field, indeed it's easier than in the symplectic case. Okay, why? Because a Poisson structure is a bivector field. So in the same way a form can eat vector fields, this bivector field can eat 2 differential forms. Okay, so now instead of feeding this bivector field with 2 differential forms, I give this guy 1 differential form, and I'm going to give him differential of f. Okay, why differential of f? Because I want to define the Hamiltonian with respect to the function f. F is a smooth function, and this gives me what? This has to give me a vector field, and this vector field is the Hamiltonian vector field. You can test this by the very definition that I gave, and you have also in your notes here of bracket in the symplectic case, that the same happens. That also happens in the symplectic case. Indeed, that's very handy definition, and that's the definition of Hamiltonian vector fields for Poisson. And now I'm going to do something which may sound a bit strange, which is I'm going to take the set of all possible Hamiltonian vector fields. How do I do this? Well, by taking the set of all functions on a manifold, okay? I take this set. This is a set, this is a distribution indeed. This is a distribution, but it's a distribution of vector fields where these vector fields may vanish at some point, okay? It's a distribution. What's very interesting about this is that this distribution is integral in the sense that Provinio's theorem applies, but in a more sophisticated way, because this distribution doesn't have constant rank, okay? But in any case, even if it doesn't have constant rank, I'm going to try to apply Provinio's theorem, which is the theorem that tells you that if your distribution is integrable, okay, then there exists a submanifold integrating this distribution. Then what I do is to apply the condition of Provinio's. I take those two guys here and I do the bracket. And well, this could be an exercise. Indeed, this is solved in the notes in the Poisson case. I think so. I also included this in the notes. Now I see there is a chat here. Take the torus, Joachim Ruger said. Okay, good. So Joachim also liked torus. So okay, he didn't like the climate. Okay, so as an exercise, I can say that this is the same as the Hamiltonian vector field of the bracket of f and g. This means, and this is quite surprising, that if I take two Hamiltonian vector fields and I do the bracket, this, of course, it's very easy to check in the symplectic case. It's super easy because it comes from the computation I did before. But to check it in the Poisson case is a bit harder, but well, it's easy to do it. The way to do it is apply it to another function and check that it's the same. And it comes from the Jacobi identity, okay? So you can check that this applied to an H is the same as this applied to an H. And the Hamiltonian vector field applied to an H is the same as the bracket. So, well, I mean, it's very simple. I mean, this tells you that the conditions of Provinio's are satisfied with except to one condition. In Provinio's theorem, we are asking that the distribution has constant. Okay, but there is a generalization of Provinio's theorem, which is due to Stefan, that requires something about this distribution. I'm not going to get technical into this because then I would spend the whole class of today just doing this, and I don't want to do just this. That tells you that this distribution is integrable in the sense that for every point, and maybe I'm going to put this in red, for every point on the manifold, there exists a submanifold, okay, of maximal rank such that the tangent space to this submanifold is the distribution at the point. And it's not going to be a surprise for you. I think that for Raju, it's not going to be a surprise that this manifold S is symplectic, is a symplectic manifold. It's a symplectic manifold with symplectic structure induced by the Poisson structure. So it turns out, Raju, do you agree with me?
So, yeah, so I can define D perpendicular, which will have the same rank, like, and D equal to D perpendicular, the involutive condition will give me integrability, like the Dirac structure.
Well, the only that's the idea. That's the idea. That's very good. That's the idea. But there is only just one minor problem, that you can do this pointwise. But with the, I mean, there is something to take care about this, because you may have a different change. I mean, this is a distribution where you may have change of rank. I'm going to put as an example of Poisson structure. I didn't want to enter into this Maybe I will put this, I will tell Pau, and what I cannot do in the class, Pau and Joaquin will do it in the problem session. That if you have the dual of a Lie algebra, okay, this has a natural Poisson structure, and then these leaves are just the coadjoint orbits. So if you take SO3, this would, I mean, just to explain this in detail would be 1 hour. I don't want to explain this in detail. I'm going to put a problem in the list. Okay, so if you take the dual of this guy, you take SO3, okay, and you write the coadjoint orbits, you get concentric spheres. That's what you get. And your coadjoint orbits are two-dimensional spheres, but there is also the point in the middle. Okay, so what I'm saying, Raju, that your argument works perfectly for these spheres when the rank is maximum.
Okay.
And it's a very good intuition, because then you have an orthogonal, and that's the way in which you associate a Poisson structure on a free manifold. And that's very convenient, the proof that you give. But the intuition that you are using is good, but when you get to the singularity, it doesn't work. Okay? But the symplectic, then what is the symplectic structure that you use? Instead of taking this orthogonal and take the area form, this is what you were thinking, you need to take just the bracket that you are given. You can check that this bracket induces a symplectic form on each leaf. So if you want the dual, because if you take the bracket, you have the bivector field, you dualize it, and this induces a symplectic structure. I mean, when I explain this, I usually take like 1 hour and a half to explain this in detail and to talk about what is the structure of these guys. So, I mean, an important example of Poisson manifold is the dual of a Lie algebra. Okay. And then if you take SO3, then this coincides with the coadjoint orbits. This foliation coincides with coadjoint orbits that are important. So these are the symplectic leaves. I went, okay, I mean, my computer is telling me, Eva, go on. Shut up and go on. So, yeah, I mean, I should advance. So here, let me be here. So what I want to say is that these coadjoint orbits have a symplectic structure, which is what is called the Kostan-Kirillov-Suryo structure. Indeed, that's worth an exercise in the list. Okay, I'm getting very dramatical because I'm explaining the basics of Poisson geometry, but we don't need to know as much of Poisson geometry. That's the idea of this picture of a guy looking at the landscape. If you have the general theory, you can look at the landscape, but we don't need to have all the general theory, just to let you know that there is a general structure out there. Okay, so here, well, this is what I have explained, that the condition of Jacobi structure is equivalent to the condition that the Schouten bracket with itself is 0. And then what is the structure of this foliation? Well, I have a foliation by symplectic leaves where I can have jumps in the dimension. For instance, here I have a point, which is a perfect 0-dimensional manifold, and then I have 2-dimensional spheres. And still I have a foliation, but this is a singular foliation. The question is, okay, you can tell me how are things differentiably, how are things, what is the, can I give, do I have a Darboux theorem for a Poisson structure? The answer is no, not in general, not at all. The best you can do, and this was done by Weinstein, and it's called the Weinstein splitting theorem, and you may think that, well, Weinstein is alive, of course, you all know this, and this was a result in 1983 or 88, I'm confused, maybe 83. Well, that all of you are younger, okay, but for somebody my age, this is not so long ago, okay? So this is not so long ago, taking into account that Poisson did his formula already in 1809, okay? So it's much later that we had an understanding of the Poisson structure locally, let it be global. So it was very late in which we were able to give a description. And the description of Weinstein can be described in this picture. Einstein told us that, well, you have a foliation, so you can think of a foliation like a book, okay? Do I have a book here? Well, you take a book or you take a notebook, okay? And you have, here I have a notebook, okay? So you think of the leaves, of the symplectic leaves as pages of your book, okay? That's a good way to think of the foliation. So you have like a partition of your manifold in such a way that for every point, there exists a submanifold, filling it the big space. And these manifolds may jump the dimension, but they are always even dimensional because they are symplectic. That's what you have to think. You have done a partition of your space into submanifolds which are even dimensional and symplectic, and this is the symplectic foliation. Now, what can you say about the Poisson structure? And this, it's a little bit taking the idea of Raju. Raju was very intuitive, trying to tell us what was the Poisson structure when you are in one of these symplectic leaves. He was thinking, well, on your symplectic leaf, if you think that it's two-dimensional, you have like an area form. So maybe you can take some kind of orthogonal and describe what is the Poisson structure using this orthogonal. The idea of Raju works very well in dimension 3, but in higher dimension, maybe you need to work a bit harder. Indeed, Einstein, he proved the following. He proved that if you are in a point of a Poisson manifold, then you know you have one of these symplectic leaves, which I'm going to, now that I have discovered that this is hiding somewhere here, okay. It's so small that I cannot see it. I take a point, okay? I know that through this point, I have a submanifold, okay? Which I take, and I know that this submanifold is symplectic. So Einstein is telling me that now I can take a different color, for instance, this mustard color that I like, or yellow, it's more like mustard color. And there exists an orthogonal, following a little bit this idea of Raju. There exists an orthogonal, but this orthogonal is symplectic orthogonal. It's not the orthogonal like Riemannian geometry. I have a kind of orthogonal of this structure with this structure. And what he observed is that the symplectic form at this point, the Poisson structure at this point, he said, you can describe it as the symplectic structure on your leaf. So if you are local, even you can take, because of Darboux theorem, you apply Darboux theorem to this symplectic leaf. And now today I feel very brave. So instead of using differential forms, I'm writing it as a bivector field. You agree with me that this would be the dual to the Darboux form on the symplectic manifold. And then you have an orthogonal where you have a Poisson structure on this slice. You have a kind of a slice, the yellow slice. And here you have another structure, pi 0. And of this structure, the only thing you know is that this structure vanishes at the point. So you know that the point has like two components, P1 on the symplectic slice, and P2, if you want, on this orthogonal, on this Poisson orthogonal, if you want. And what you know is that this vanishes on pi 2. That's the only thing you know. If you want to write it down as a bivector field, you can do this, but it's not very helpful. You can write, you're going to have some functions. You have a manifold that can be of any dimension, and you can have some local expression. Okay, this manifold is of dimension n minus 2k. You have some functions on your manifold that write down in coordinates time, some local expression. And the only thing you know, and that's the way a local bivector field looks like. But the only thing you know of this Fij is that they are going to vanish at the point. Then, of course, you can apply, I mean, people after that try to apply linearization theorem, non-linearization theorem, and quadratization theorems. And sometimes you can linearize this transversal Poisson structure, but sometimes you cannot. I mean, there is a theorem by Kohn that if the transversal part has, of course, this transversal part, you can take the Taylor expand of each function, and you can take the linear part of this function. It's an exercise, an interesting exercise to check that the linear part itself is a Poisson structure. And if this linear part, because any linear Poisson structure can be represented by a Lie algebra, if this Lie algebra is what we call semi-simple of compact type, which means that you can integrate with a compact group, then in that case it's linearizable. Already, as you realize, just to say this linearization theorem by Kohn, it took me a while and a little bit of thinking. So it's hard to find Darboux theorems, a nice expression for general Poisson structures. So this is a bit disappointing, right? Because you start a thesis, if you start a thesis in Poisson geometry, you like to prove things, right? And this leaves you a little bit far from, it's not, it's, I mean, it's a very, it's a bit disappointing in a way. But there are good news. That for our structures here, there have to be some good news. And for our structures here, which are the B Poisson structures, the good news is that we have a Darboux theorem. Okay, let me once define now very clearly. I gave some examples. I said that some singularities were reasonable, but I didn't give a definition. Let me give the definition of B Poisson structure. B Poisson structure is known in the literature by different names. It's also known as log symplectic structure. And why it has two names? Well, because the origin of log symplectic structures comes from algebraic geometry. The motivation comes from algebraic geometry, and in algebraic geometry, the log complex is very well understood, and that's the reason why when we started to work with these objects, with Victor, we call them B Poisson because of the motivation of manifolds with boundary, and because Melrose already had been working with B structures, okay? But then at the same time, Marco Galtieri, and this was very funny, because this was in 2010, I was giving a talk about this in the Poisson conference. I was young then, this is a long time ago, this is 11 years ago. And then at the same time, Marco Galtieri was giving a talk, right? And then he discovered in my talk that we were working on the same thing, but he was calling them log symplectic. At that moment, we still didn't post, we hadn't posted the paper on the archive. And then so Marco Galtieri and I were working with the same objects from different points of view. And this was a very rich experience because we end up proving results from different perspectives, some of them very different results. So this became a very attractive class of Poisson geometry for which you could try to ask the kind of questions you ask in general for general Poisson manifolds, and you could get some satisfactory answers. So ever since 2010, many people got interested in these structures. Still still there are a lot of works going on, and I'm happy to see sometimes on the archive like recent paper by Stefan Waldman, still working new aspects of these manifolds. And why are they attractive? Because they are easy to understand. What is a B Poisson manifold? Now I give the formal definition. I have a Poisson structure, okay? And here, well, today I'm going to assume that it's oriented, but it's not necessarily oriented. You can define this Poisson structure on a non-orientable manifold. Today, let's just for the sake of simplicity, assume it's oriented. Indeed, when Victor and I started to work on this, we started to think of the oriented case. But then, of course, you are tempted to take quotients by discrete groups. So non-orientable examples appear naturally. So let's assume today that we have an oriented Poisson manifold, that I need this to be even dimensional of dimension 2n. And then I have a bivector field, pi, okay? Now, the condition that we are requiring is that the map that sends every point on the manifold to pi n, which is, observe that pi n, okay, pi n is, this is a mapping, okay, pi n, I can look at this as a section of this bundle. Okay. So what I require is that this map here is transverse to the 0 section of this bundle. Okay, transversality makes us think. What does this condition mean? Let's start with an easy example. Let's take n equal to 2. If we take n equal to 2, this is telling you that the mapping that sends p to pi of p, because then well, when I take n equal to 2, n equal to 1, or the dimension of the manifold equal to 2, this would be the first case. Then I'm sending p to pi of p. So what I'm requiring is that pi of p, so this is a 2-dimensional manifold. So let's assume that I take some local coordinates of this structure. Okay. If I take local coordinates, then what I obtain is some expression in dimension 2, right? So in some local coordinates, some function of x1 and x2, partial x1, partial x2. That's what we get. That's pi of x. Okay. What we are asking is that this function, that this pi is transverse to the 0 section of this bundle. This is equivalent to what? To the function. Here I have a function. So what I need to require, because of the regular value theorem, this is equivalent that this function is either x1 or x2, that it's linear. That's the condition. I need this function to be linear. That's the condition I need. Okay. And because, if you want, because of the regular value theorem, I can always assume that this function is equal to x1. So if I have a 2-dimensional B-symplectic manifold, locally, and this is the proof, there exists some local coordinates such that pi locally can be written this way, locally, not globally. So I am proving indeed, just by hand, the Darboux theorem in dimension 2. When I'm higher dimension, in higher dimensions, pi n, what it gives you is the equivalent of the volume form. So when you do pi n, you get the same. You get a function of all the coordinates that multiplies the dual to the volume. So what you require is that this function is linear. You can require that this function equals x1. That's the condition. Sorry. This is telling me to advance more quickly. That's the condition of transversality. Okay. Are there any questions? I mean, the definition is like, okay, as always, you do the definition, is correct, it's mathematically correct, but you need to think what transversality is telling you. It's equivalent to saying, this is the same as to say that 0 is a regular value of this mapping. Okay. And then if 0 is a regular value of this mapping, because of the regular value theorem that I'm assuming today that everybody knows, the set given by the zeros of this function is a smooth submanifold, okay? Which, of course, if I count, it has to be of codimension 1. So it's a manifold of dimension 2n minus 1. And that's what we call the critical hypersurface. That if you look at my first paper, we were calling it the exceptional hypersurface, but then discussing with Marco Galtieri, we thought that the good notation was critical hypersurface. Okay, and this is B or log symplectic manifold. It's the same. When you look at the holomorphic case, there are some small, tiny difference. I mean, log people also look what we call the hyperbolic case, but not today. I mean, we'll not talk about this today. Again, now one thing you could take is to take the list of Arnold. Okay, the other day we had the honor to have here Boris. I don't know if Boris is around, but let's talk about Arnold. One wise thing to do is now take, instead of the, let's say, the first simplest case in which this doesn't vanish, it's the linear case. Now let's take singularities of order k. Let's take the list of R0 of singularities, and we find all sorts of singularities here. We could take elliptic singularities, all of them, and they are very interesting to study. Today, I just want to consider the case of singularity in which I have a singularity of order m. So locally, in dimension 2, it looks like this. And these are called BM symplectic. These are called BM symplectic or BM Poisson manifolds. Indeed, now there are some details in which I want to discuss. When we started to study this, you can study these structures with different assumptions. You can assume that you have a function, and that's what we did with Victor, such that the z equals f equals 0, that you have a global function on your manifold. Of course, you have always a local function. Or you cannot assume this. You can assume this or not. And then there are some tiny differences. For instance, Jeff Scott, who worked in his thesis, he completely worked out the theory of BM Poisson manifolds, at least the study of toric manifolds there. And then Arnaud Planas worked out in his thesis the theory of KM manifolds, KM theory. We had a KM theory for B manifolds with Jeff, but we improved it with Arnaud. And Arnaud also worked out he extended the theory also to non-oriental manifolds. He classified, for instance, all two-dimensional symplectic manifolds admitting a BM Poisson structure. He wrote a beautiful, beautiful thesis. And these are other singularities we could consider. Okay. So one question is, okay, now I'm going to test what we understood about the symplectic foliation. I'm going to ask Raju. I'm asking Raju all the time. I could ask Marcello, maybe Marcello, you want to read? Marcello has the camera on. That's a danger, okay? I know that you are listening to me. So, Marcello, what is the symplectic foliation for the AB symplectic manifold? Well, it's described here, but let's say if I give you a particular example, for instance, of the sphere, here I have a space for nodes. I'm going to give you a B symplectic, a B Poisson structure on a two-sphere. I take pi to be h partial of h wedge partial of theta. This is B Poisson, no, because it's two-dimensional, and we said that the condition is transversality. This is equivalent to having a linear function. So this is a B Poisson structure. Now the question is, what is the symplectic foliation? As it's Poisson, maybe I can describe the symplectic foliation. Marcello. So let's think. If I'm here, I'm away from this critical set. So this H is going to be positive. This means that this is going to be like an area. You agree with me? So yes. This means that, right, Marcello? So this whole northern hemisphere is going to be all the north hemisphere. It's going to be without touching.
Without the equator, yeah.
This is going to be an open symplectic manifold. You agree with me, no?
Yes. So
this is an open symplectic leaf. We did half of the sphere, okay? Let's go on. What else? We can do the same for the south here, right? H is negative, okay? But the important thing to have a symplectic structure is that it has an area form that it's negative, okay?
Yeah. So we just take the bottom up as well.
So we just take the bottom, perfect. So here, what happens? Okay, this is another open symplectic leaf. Okay, good. This is a leaf, leaf 1, leaf 2. And now let's look at the equator. What happens on the equator?
Because the equator is exactly the set in which we have pi equal to 0, right? The set Z that we
Exactly.
mentioned before.
Yeah. So we have pi equal to 0. So exactly. That's very good, Marcello. So this is the example, the silly example I was mentioning, where you have the Poisson structure induced on the critical set is 0, right? So the symplectic leaves, that's a very good point, the way you put it, I like it, are just these points on the equator. So the points on the equator are the symplectic leaves. So that's the symplectic foliation. Fantastic. Now, if we go to higher dimensions, of course, we need to understand examples.
Maybe it's something stupid, but when you actually called me, I was distracted thinking about that. So that may be a good point to ask you. It's before getting here to the B structure. When you mentioned the Poisson structure, you mentioned that it's the one in which you have the special bracket of pi with pi equal to 0. And you mentioned that the bracket actually goes up one dimension, right at the beginning of the lecture. So you get, if I take a bracket with 2 bivectors, I get a 3 vector. I did understand correctly?
Yeah.
So
but this 3 vector is 0. Yeah, that's a good point.
My question was, does it mean that any bivector in a 2-dimensional Poisson manifold, so in 2-dimensional manifold is an actual giving you a Poisson
exactly
manifold?
That's wonderful. Indeed, that was an exercise in one of the lists. That's wonderful. That's a good observation.
I'm very sorry.
So
that's
look
at that.
Marcello, that's fantastic. Marcello's theorem.
Sorry.
Marcello's theorem is that any, and that's great, okay, that any 2-dimensional manifold, okay, any bivector field, that's fantastic indeed. Indeed, this is going to be, this was used in the list of problems. That's fantastic. So now I'm doing the work for Pau, and that's very good. So any bivector is going to satisfy that pi equals 0. And that's precisely how you prove it. That you say, well, this guy is a 3-vector field. I didn't want to get into multi-vector fields, okay? It's not that I don't like them, it's that I could spend my whole life there, okay? But this is a 3-vector field. And then in dimension 2, there is no space to have a 3-vector field because you have 2 coordinates. Therefore, this guy, the only possibility is that it's 0. That's the only way. And that's how you prove that any bivector field on a 2-dimensional surface, and that's your theorem, is a Poisson structure. That's how you prove it. Fantastic. That's very convenient. Because there is exercise 1.7 in the list is going to use this. Okay, so Marcello's theorem, and it is very convenient. Now, this will be used in the list. That's a very, very good observation. Of course, here I could talk about, indeed, there is a way to construct a cohomology, which is Poisson cohomology, when you take a multi-vector field, let me call it B, and you do the bracket with pi. This defines for you a cohomology, but instead of being a standard cohomology, you take, you take multi-vector fields, okay? So instead of sections of powers of the cotangent bundle, you take sections of powers of the tangent bundle, and you can define Poisson cohomology using this guy. But
so it will
Poisson
be
cohomology would be, yeah, Raju?
Will it be Hochschild cohomology?
Yeah, I mean, Hochschild cohomology, we are entering, don't take me to that, because I enjoy a lot all these. I'm addicted to cohomology. It's very interesting. Hochschild cohomology, we have a list of cohomologies, and some of them are equivalent and some of them are not, depending on the manifold. But that's a wonderful, of course, it's connected to hot sheet chromology.
Okay, I'm not going there, but a related question, as Marcelo put it, like this pi equals to 0, this Schouten-Nijenhuis bracket. So
Yeah.
does it has to do with the integrability? Like if it doesn't
Yes.
satisfy? Ah, okay.
Okay, this is indeed, okay, that's a very good question. I mean, that's a very good point. Indeed, I often call this integrability condition. I mean, and we call this integrability condition of this because it's an integrability condition whenever you have a bracket equal to 0. And indeed, it's good to think about this. If you consider the set of brackets and you look at this integrability condition, this set is very small. This is telling you that most of the tries you are going to do are going to be out of the set because the set, when this is equal to 0, has 0 measure on all the set. So this means that a vector field to be Poisson, you need to be very lucky because if you want, this condition is a closed condition. So in particular, when you perturb a Poisson structure, you are out of the, you usually are kicked out of the realm of Poisson structures when you do a perturbation. That's why Poisson geometry is so much more difficult than symplectic geometry and contact geometry. But well, one good news is that our B Poisson guys are the good guys. They are easy. For B Poisson, we can study perturbations. I mean, well, as you see, I'm like, you ask me questions, I get very excited about this. But we have a program to accomplish and I'm having a way. Let me go back a little bit to the syllabus because I'm getting overexcited with this. I wanted to tell you that we have good news for you. The first one is that we have a Bidart theorem. This is wonderful. This means that, okay, if I look as a B Poisson, as a Poisson structure, and I think of the local normal form, I might be tempted to think that because Weinstein theorem is so complicated, I don't have a local structure. However, because the class of structures I'm considering is almost symplectic, because look at this wonderful example that we made here. The symplectic leaves are dense. That's what happens. This means that outside the critical set, I'm symplectic. I'm Poisson, of course, in particular, because I'm symplectic, but I'm a little bit wilder because I declare some leaves that are different, but in codimension 1, okay? So the message I want to convey is that we can do many things with these Poisson manifolds. We can even play football with them. One thing we can do is to prove Darboux theorem. The proof of Darboux theorem was not scheduled for today because I will use the path method, and this is scheduled for next week. Let me talk about examples. It's important to have examples in mind, and I think it's important to have examples that, you know, maybe come more naturally from other examples you saw. Well, one example are all these examples of Radke. I call Radke surface when I have a surface, and by the observation of Marcello, any bivector field on a surface is going to be a Poisson structure. This is fantastic because then you don't need to check anything. And and then you consider a codimension 1-2 manifold, and there you go. These are, I mean, you can consider different connected components here. You may have different connected components. This is tending, take me back. I could have different connected components here, where I could have maybe different connected components. It doesn't matter. The important thing is that this set is a codimension 1. So there are natural questions. For instance, what is the structure you have induced on this set? And we already saw from the example of Marcello, and this happens in any two-dimensional case, that what you're going to have is a set of points, is a union of circles where the symplectic leaves are the points, and the Poisson structure induced in the two-dimensional case is 0. But what happens in higher dimension? The Poisson structure is no longer 0. Okay, but it has some maximal leaf, like it has some constant run. So I'm going to take as an example, and that's a classical example from foliation theory. I'm going to take I have a space for notes I prefer to use to write it down. Let me take a codimension 1 foliation, So for this, I'm going to need a manifold of dimension 2n minus 1. And this manifold, which I make a picture like this, I'm going to assume that it has a symplectic foliation. The symplectic leaves are going to be blue, and they have dimension 2n minus 2. So I assume that I have a manifold, this is M, and has a codimension 1 symplectic foliation. I'm sure that all of you have a favorite example of symplectic foliation. But here it comes as strength, as something that doesn't look very, very harmful. And this is a problem in the list, by the way. But I think it's good to think about it, even if it's in the list. I'm going to assume that I have a transverse vector field everywhere, which we call X in this example. It's a vector field which is transverse to the symplectic foliation. This symplectic foliation, I call it S. Then when we have this, automatically, one thing I can do is first, when I have a symplectic foliation, codimension 1, okay, I can think that of course, I have a Poisson structure. It's a particular case. And I call this Poisson structure pi. Then one thing I can do is now I take a product of this manifold N. I could do a product with R, but if I like compact examples, I take a product with S1. What I do is to consider a function, a linear function in theta. I could think like a cosinus, okay? And then I take this vector field X, which is global, times partial of theta. That's an exercise in the list, and that's an interesting example that this defines a Poisson rank, a B Poisson manifold. And indeed, that's the model. If I have any B Poisson manifold and I look at the critical set is going to be like N. N is going to be like the critical set. And what happens is that the Poisson structure induces on Z a codimension 1 foliation. This comes for free, okay? Because if you write the condition that pi is transverse to the 0 section, you get automatically this. You can do this by using Weissen's theorem. Okay, when I looked at this example, when I was first thinking of this, I got overexcited because a part of me comes from foliation theory. When I started to do research in mathematics already as an undergraduate, I was reading foliation theory. So I knew that there was this class, this magic class of codimension 1 foliations where people could do many things and there were interesting theorems there. So I certainly got overexcited by this. Because you can do many things with codimension 1 foliations. But the truth is that the existence of this transverse Poisson vector field is a strong requirement. Indeed, you always have this. When you have a B Poisson structure, and that's a theorem we proved, and we will prove it next week. Now I'm just describing it because the proof uses the path method, and I will say how to prove it. If you have any B Poisson manifold in a neighborhood, your manifold in a neighborhood of the critical set, your manifold is going to look like this example. Okay, where do you use that X is Poisson? And that's an interesting, this is an exercise in the list that when you want to check that pi is equals to 0, now we cannot use Marcello's theorem because we are not in dimension 2. We need to put our hands in the computation. So of course we can use, well, we have pi prime. We know that pi is equal to 0, and we need to check that pi prime. Then the thing we need to do is that this bracket involves to compute the bracket of X with pi. But this is the same as the Lie derivative of X with respect to pi. This is equivalent to saying that this is a Poisson vector field. So we are going to need to use this condition. And we need to use, of course, the condition that, of course, why this bracket is 0? Well, because the theta coordinate has nothing to do with the coordinates on N. It's an external coordinate, okay? Therefore, its Lie derivative is going to be 0. This is the Lie derivative. Pi doesn't depend on theta, therefore the Lie derivative is 0. If you use these two conditions, I have almost solved for you an exercise in the list. And then this exercise in the list is a theorem. Any Poisson manifold can be written this way. Why? Moser's theorem. This will be seen next. Another exercise in the list. I took this exercise. I borrowed this exercise from my friend Marco Galtieri. Okay, we can consider this on RP2. Then this would be an example of where you can put things on non-orientable objects if you want. And if you take this real elliptic curve, okay, then this descends in RP2 to a B Poisson structure with two different connected components. This is another exercise in the list. What's nice about this example is that it obliges us to think a little bit further because this works on RP2, but you could also think of this working as an holomorphic structure on a different complex coordinates. This example, you can elaborate on it as much as you want. It's a very nice example. It's an exercise in the list. Okay, now I am over time. Of course, I had decided, I don't know, yesterday night, I had decided it was a good idea to prove what is the structure on Z. And the truth is that the structure on Z is not any codimension one foliation. It's a very particular type, because having this transverse Poisson vector field, in a way, if you use the flow of this transverse vector field, what you can do is transport by using the flow of the vector field X, you can prove that the critical set is always a mapping torus. And this is indeed a theorem. This is a theorem that we proved. And indeed here, I mean, there are some slides. I'm going to skip these slides. There are some slides in which I study all this codimension one foliation. I think this is rich, but I will reintroduce it somewhere else using the RAM Chromology, because as I said, in the heart, I am an algebraic topology, so I look for invariants. But I think that the important thing is that the condition that this Poisson vector field is transverse to the foliation, indeed you can write it down as a cohomological condition. And that's funny. Well, you don't need this, but it's funny because it's related to foliated cohomology. I'm going to skip it. But what's important, well, this is related to a theorem of Tisler, but what's important is this theorem. This describes completely what is, in dimension 2, we saw that Marcello was giving us the description of what is the foliation. In higher dimensions, the critical set is always a codimension one foliation, but not only that. The manifold itself, if it's compact, it's given in the following way. It's given as the mapping torus, okay, of a simplex homomorphism. This means that we take the product of one of the symplectic leaves with 0, 1, and we glue phi of 0 with phi of 1. Indeed, in the proof, what we do is this existence of transverse Poisson vector field that you can codify in a nice way. You can understand this condition in a nice way by the vanishing of a Godbier. I mean, you can understand this by the vanishing of some foliated cohomology classes. In particular, the Godbier class has to vanish, but also two differential classes have to vanish. This is something that we don't need. And maybe it's enough to remember that because in the proof, you just need to flow using this transverse Poisson vector field. And then you can prove that the critical set, the Poisson structure of the critical set, I mean, not only the Poisson structure, the critical set itself is completely understood. So mystery is gone. The codimension one foliation is very simple. It's just the leaves, okay, of a symplectic mapping torus. So you can think it's almost like a direct product. It's not a direct product. You have to glue. It's what we call a mapping torus by using a symplectomorphism of the leaf. Okay. Now classification issues. Well, I mean, yeah, today I'm very slow because my class is supposed to finish now. And look, I still have to look at the same. I mean, today I did less than what I expected, but I think this is a good point to finish the class because I'm over time, first thing. Second thing, I wanted to describe the dual part, but I spent, well, a long time looking at Poisson geometry. I think this was needed because not all of you knew about Poisson geometry. But okay, on Monday, I need to do many things on Monday. On Tuesday, next Tuesday, the initial plan was to talk about the Moser lemma and then to talk about, again, to look at the example of the restricted free body problem, okay? What I think I will do on Tuesday is to talk about singular forms that today I couldn't do, okay? Because I need to talk about singular forms, about desingularization, and about Moser's theorem. That's a lot. So I'm going to stop here. And I think this is a good place to stop. I will continue next Tuesday, but I would like to know if there are questions at this moment. I mean, do we have some questions? Let me stop sharing. Do we have some questions? I mean, you may have some questions because today I have been stirring up a lot of new material like Poisson geometry, okay? Let me tell you that I gave a very basic introduction to Poisson geometry, but in the notes, this is a bit more extended. In the notes, you can find a bit more. These notes are some notes that we started to write with Pau and Cedric, no, for the master course. And then we use them. And now we are going to keep on improving them until they are good. But I think that maybe you want to look at this Poisson part. So, okay, next Tuesday we will go to the singular forms. The singular forms is going to be, the conclusion is that when we zoom in, we use a singular form, coming back to this idea of the flower. We have been just walking along the garden of Poisson structures, but now we need to zoom in and concentrate to say things about these V-symplectic forms. And I need to introduce this, I need to talk about V-vector fields. This is serious stuff that requires a lot of concentration. So I don't think it's a good idea to do it now. Huh? I will start next class with this slide. Questions?
Excuse
There is
me,
a question
Professor.
there. Yeah.
I have a question. I
Okay.
don't understand what you said. There are structures that be taken as a symplectic form, which is not a symplectic form. Is there a simple example to illustrate?
Yeah, you say, can I take an example which is not a symplectic form?
Yeah.
But I have a two form. You want a structure which is Poisson and not symplectic, or a two form? What do you want?
Yes, I want a simple example to illustrate it.
To illustrate, okay. So we want an example. Let me share again. You want an example of a form that cannot be symplectic, right?
Yes.
Okay. For instance, okay. Let me give you a simple. I mean, one simple example is the following. It's a little bit inspired by Raju's. Let me share again. Share. You asked me, what's your name?
My name is Li Jiayang.
Li Chayao. You were asking me also the other day, right?
Yes.
It was you. Okay. Nice to meet you.
Nice to meet you too.
Okay. Thank you. Let me share this. Let me see if I'm able to. 1 second. Second that I need to close this. Okay, now screen, zoom. Let me write on a simple structure that is not symplectic.
Yes.
So I could also take a differential form. I mean, one easy reason. Let me take just notes. Okay, I can also take a new note. Okay. So if I take, for instance, now assume I'm going to take a structure that is going to be useful also for this codimension one foliation. I could take other more sophisticated examples. Now imagine that I take this form. These are two forms, but I take it on R3. I'm going to take a very simple. So this would be an example because it's not, this structure cannot be symplectic because we have the problem that the dimension of the manifold is 3. But an interesting thing about this example, and this can be also useful to understand this last thing I was explaining, is that I can think of R3 as foliated by copies of R2, right? I can make a picture, and this is the OZ, and this can be copies. And on each one of these copies, this is a symplectic structure. So indeed, this example is good because this form on itself on R3 is not symplectic, but the restrictions to this form, to each one of these slices where Z has a constant value, okay? When I take Z equal to constant, this automatically is symplectic. And indeed, if I look at this collection of leaves, this is like the book. This is like I have a collection of leaves, and this is like a symplectic foliation. So this is an example of a form on R3, which is not symplectic, but induces a family of symplectic foliation. So this is a useful example. In this example, I'm going to leave you an exercise to think that in this example, the question is, do I have a vector field which in the do I have a vector field X? Oh, do I have a vector field X which is transverse to this leaf and which is Poisson? I'm asking you a difficult. You understood this example. You are convinced by this.
Yes.
Okay. Now I take this vector field. Okay. And automatically this, by the way, this I can think of this as a Poisson structure because I take the simple Poisson structure, this one. Okay.
Yes.
Now this vector field, okay, this Poisson structure, I have it defined on R3. And this vector field is an example of Poisson vector field transverse to all the symplectic leaves. So here we have an example of codimension 1. So this guy is not an example, it's an example of something which is not symplectic, which induces a codimension 1 foliations, and which can be the critical set of a Poisson structure. So I'm giving you, so the answers I'm going to ask you is, do you know if this guy is a Poisson vector field? How would I check it? I need to check that this is 0. And in order to check that this is 0, that this is, indeed we have the program session next week, but it would be convenient to have it now, right? Because we need to work a little with vector fields. But by vector fields, we work with them as we can. We work with them as you would treat a vector field. You just take the lead derivative of Z with respect to X, wedge partial Y, and then you do the partial of X, wedge partial of Z, partial of Y. And surprise, surprise, all this is 0, and therefore this is 0. This is the kind of computations you do to check that a vector field. So, I mean, you asked me a question, I answered the question, but I also gave an example of something that can be visualized as the critical set of a Poisson structure. Was this clarifying?
Thank you. I
Okay.
get it. I get
Okay.
it. Thank you, Professor.
Thanks.
Thank you.
I mean, everyone feel free to send me emails. Thank you very much for participating in the questions, and feel free to send me emails asking questions. I mean, since we have lost some people in the way, because I think they are probably connected to the former one, or I don't know, or they were people from the Poisson geometry who didn't get the message from Nikita. So I hope that, well, the place in which we are is a good starting place for the next class. I'm a bit beyond my schedule, but I'm happy that people are participating. So keep on participating and send me emails whenever you want. Okay,
I have one last question, Eva.
Yeah.
You mentioned that for S4 there is no symplectic structure. So I wonder whether this is a generic.
Repeat, Raju. I didn't hear you. Can you repeat again? Yeah.
Sorry, for S4 you mentioned that there are no symplectic structures. So I wonder whether it's a generic feature for higher dimensional sphere like S6.
Yeah. Exactly.
Or
yeah, you are totally right. So
okay.
exactly what happens on S6. So we know that, so as a conclusion of that proposition that you prove using a Stokes theorem that it's in the notes, we know that the symplectic form defines a class on H2, which is non-vanishing. So I go to my doctor in algebraic topology, and I take him a sphere, and I take him all these spheres, and the guy is going to tell me, I'm sorry. I said, what? H2 always vanishes for this sphere. The only sphere where this doesn't vanish is S2. So I'm also a fan of spheres, but the spheres can only be symplectic in dimension 2. And now the question is, can you put a Poisson structure on a sphere? Yes, you can. Of course, you can put the zero structure. But now, this is a question to think, okay? The list of problems is a list of questions to think, but I'm going to give you like a philosophical question, okay? Because I think, Raju, you like philosophical questions. Okay, so I'm going to take S4, and I'm going to ask you, can you find a structure on S4 with dense symplectic leaves? Can you find, does there exist? There exists. That's a question for a top mark of the course. Does there exist a Poisson structure on S4 with dense symplectic leaves? Why I said dense symplectic leaves? Because, well, symplectic, I know it cannot be. In the list of problems, it says that bisymplectic cannot be, but still, I don't know, can I find, maybe by taking out a couple of circles that's cross on the sphere, on S4, can I still find an example of a structure which will be more complicated than B? And that's an interesting question. That's almost a philosophical question. I know the answer to this question, but I'm going to bite my tongue. No, I'm not going to tell you which one to look for, but it's a simple one. The answer is yes, but think of constructions. Think of this.
Okay, thank you.
Think of this. This is a good exercise. That's a good exercise. I mean, think of the simplest one you could think of. And there are examples. So if you look at last class where Chung asked me about examples, I said elliptic, I said hyperbolic. Okay, well, finally I'm giving you the hint. Try hyperbolic singularities on the sphere, on S4, and it works. Hyperbolic singularity means that the Poisson structure looks like this locally, of this sort. And maybe with some other coordinates. You can find, and it's possible to find some kind of a structure like this and some kind of a structure with more vanishing points, even X and Y here. Okay, but I think it's good that you think of this. It's very interesting. It's a whole world out there about to understand this abstraction. And of course, behind an abstraction theory, there is always a cohomology. So it's easy to, well, I mean, it's easy. It's possible to find cohomological abstractions for a manifold to admit a particular type of Poisson structure. Of course, we know that zero structure is always there, but let's say I want now to restrict the class of structures. And that's what we call abstraction theory. Okay. Okay. I think that the host, I mean, Chung was our host, but he's teaching now. He sent me a message, and he has to teach, so he has teaching now. So we don't have a host, so we have finished what we want. I mean, if there are more questions, you can send me emails. Yeah.
So I have two questions basically. So the first one is
Who's talking? Who's talking? I mean, who? I mean, I know. Who is?
No, is Yuli.
Okay.
Do you hear me?
Yeah, Yuli. Hi.
Okay,
yeah.
great. Okay.
I can hear you.
Yeah, I have two questions.
Yes.
So the first one is I somehow have the feeling that when people talk about log symplectic manifolds, the critical locus is allowed to have multiple irreducible components. Is that correct?
Yeah. I mean, in the log case, you may have self-intersections. Okay.
Sure. Okay.
You may have
so
self-intersections.
Are we going to maybe say a few words about this later in this course?
Yeah, indeed, that's the kind of a structure that S4, now I'm giving the solution almost to Raju, I'm giving a big hint to Raju that you can construct this on S4. Yeah, we're going to consider self-intersections. Yeah.
Okay.
I like to look at these guys indeed as a differently algebroid. I look at them as differently from Marco, because I look at them, I can associate the first thing I'm going to explain the next day is how to look at these structures as differential forms. That's the point where I stop, because it's a point that requires some thought. And the interesting thing is that here I can associate a Lie algebroid. So whenever I can associate a Lie algebroid, I can define what Nest and Sigan consider in the late 80s, that they already defined what is an asymplectic manifold. This is in an old paper about holomorphic Poisson structures by Ness and Sigan, that it was a little bit forgotten, but they introduced this name to this asymplectic. I didn't do this. I could have done this because my name is Eva, but this would be too selfish. It's not my idea. It's not me who coined this, but E from Lie algebra. So in that particular case, you can think of a Lie algebra. Okay, I like to think, yeah, you could define this a log symplectic, because if you think about holomorphic structures, you can also think this as bisymplectic holomorphic somehow. But I like to think this as an asymplectic manifold. However, in that case, let's say there are abstractions that work quite differently. If I want to understand this kind of self-intersection, if I don't want to distinguish, as they don't do in the log symplectic, between self-intersection and not, then the abstractions, I mean, you can give, what I'm saying is that yes, you can give more accurate abstractions that the ones they have in log symplectic. This is something that we started to study with Jeff Scott, and we wrote a small paper about this. We have some ideas that are still not written down. Jeff Scott, unfortunately, I mean, he was, well, I mean, life is like that, right? He was paid so well at Google that he left academia. But we were like, I mean, there is a way to study these abstractions cohomologically, and this cohomology lives exactly in what we call the ecohomology. This is the starting point of my next class, but I wanted to start little by little, because here there are people of different levels. So I wanted to start really by ecohomology, and then leave these other cases for later on. But yeah, Julie, I plan to look at this.
Okay. And then my second question is, so going back to B symplectic.
Yes.
So maybe for simplicity, we could assume that our manifold is, let's say, projective smooth variety over the complex numbers, etc. Now,
Yeah.
since it's Poisson, it makes sense to quantize it. So can one
Yes.
classify all possible quantizations?
Yes.
And in what
It
sense?
is. Yeah, I mean, this is something that I have worked out, but it's not in the program of this course. I would be happy to give some extra lectures if people are still up to it about the quantization, because quantization is a whole interesting world. So to start with, this guy, I mean, there is the first, like you have like a first model. I mean, you have the formation quantization. So the answer is yes, this has been studied, and more is to come, because Pau who's here, we're still working on more on this. So we are very happy about this. Let me do this now that I learned from Marcello how my computer works. Thank you, Marcello, that I didn't see the small hint. Let me say just a few words like advertisement. Okay, I didn't plan to cover this in this course because I wanted to focus on these applications to celestial mechanics and to symplectic topology. But let me give total like Nest and Sagan, and they are not cited enough in this business, started to consider the formation quantization of manifolds with boundary, and they were already considering the problem of the formation quantization. In that paper, I mean, they did the case of manifolds with boundary, symplectic manifolds with boundary, but if you read at their paper with care, you can easily translate this to the formation quantization of bisymplectic manifolds. And then you have other models, of course, of quantization, okay, other than the formation quantization. Of course, the formation quantization was very popular because of Kontsevich, bisymplectic manifolds, but you know, if you are a classical person, you may like the geometric quantization. And well, maybe I say something about this now that I have a way to say something about this. This is something we worked out with Victor Guillemin and Jonathan Weitzman already in 2018, where we gave a model. So the conclusion is that we have we gave a model rather than the classical geometric quantization. We used what is called formal geometric quantization, which was, let's say, a functorial approach to geometric quantization for manifolds with boundary, where things were expected to go to infinity. And the big surprise is that we obtained a finite representation space. Here I'm talking in wild, I mean, the other students don't worry. But I think you know what I'm talking about, okay? So this is finite representation. So this is what we proved. We get some finite representation space, and we need to, in our proof, we assume that we have a torus action. Not necessarily toric, we have a torus action. We require that the torus action has non-vanishing modular weight. We did this finite representation space, and later on, much later on, somehow Lee, no, somehow, what's his name? Yeah, somehow Lee, and I don't want to forget anyone, and Braverman, somehow, and Loizides. I cannot pronounce their name. Loizides, I mean, former student of Mainbrenken. They answered, I mean, there we were asking a question, do you have, I mean, one of the questions is, can you find an operator such that the index of this operator gives you exactly your formal quantization? That was a question that we left open in our paper. And then these guys answered yes and constructed it. And basically they were using the operator they were using the operator of Melrose for manifolds with boundaries. So it's very interesting to see what they do. We did it in a different way. Our approach was very hands-on. I mean, it was very short. It's a paper of 8 pages, I think, when we wrote. And their paper is like 30 pages, but they gave an answer to this. And later on, like right now, well, let me do a spoiler. Right now, I can say that we completely understand in a very clear way the toric case. The toric case, we have a very nice interpretation of this finite, formal geometric quantization. Indeed, and we have a theorem that says that this formal geometric quantization coincides with the geometric quantization of Guillemin and Sternberg, so counting Bohr-Sommerfeld leaves, and that's a new result. This is a result with Paumir, myself, and Jonathan Weitzman. I mean, I'm announcing this. Jonathan Weitzman would kill me because this is not on archive, but this is something we have proof, and it's almost there. I mean, I hope that, I don't know, by the end of the month, it will be online, and this is a joint result. And so we have now, let's say, what's nice about this paper that we are working on is that we have, let's say, a very clear model where we can draw this quantization with polytopes. So that's the kind of result. So I didn't plan to talk about this in this course, though there is a connection, of course, between geometric quantization and Bohr-Sommerfeld leaves and the polytopes. This could be a nice continuation of this course. I would say that this is a different course because this would be another course. I would be happy to do this course maybe later on, right? Because it takes a lot of energy to prepare one course like this. But I don't know, maybe Pau would be up to doing a course. We could do a course on this with Pau together. Pau is like crazy learning all this very quickly. And but I didn't plan to explain this. But yeah, these are some results. Some other people are working on this and obtaining, for instance, Shamar. Now I don't remember. Well, Shamar also got some interesting results concerning the geometric quantization, okay, without assuming the existence of toric actions. But toric actions makes things very beautiful, as I said, because you have then a way to look at your solutions graphically and make a picture with polytopes, which is very nice. Okay. So I don't know if I answered your question.
Yes. So your results depend on a torus action, right? So, but in general, if I don't have a torus action, then can I at least hope for something as nice as this result of Bezrukevnikov and Khaledian?
Yeah. I mean, these other guys don't assume. These other guys. So I mean, I mispronounced his names. Braverman. I don't think Shamar assumes there is a group action. I don't think he assumes toric actions. I think they do it without this assumption. You can do it. Yeah. Okay. They do it. Okay. But this is a result. I should prepare. I mean, I didn't plan to explain this in this course. This is for another course. Of course, this is very interesting. Yeah.
Okay, great.
Yeah. So I can give you, I can give you the if you look at Shamar's, and my iPad disconnected. Okay, well, never mind. I stopped sharing. So if you look at the papers of Shamar, I can try to find this for you and put it on put this information next Tuesday here on the chat. There is a recent paper of Shamar, one of the last papers. He did it without this assumption. It's important to know that with our paper with Jonathan, we use an assumption also on the cohomology, on the B-cohomology that I will explain here what is B-cohomology, that it's not necessary, but it simplifies, all right? Let's say our paper was extremely short, and some of the conditions can be easily be dropped. That's true. But it's true that our approach was really making use of the quantization commutes with reduction. That's why we were using the torus action.
Okay, okay, thank you.
I don't know if this brings some light. I mean, the other students must be completely lost. I mean, the ones that are still here around, because I'm talking to you, Lee, because I think he knows all this, and I'm using a specific language that it's not just one that you need to know to follow this course, okay? Yeah, so Yuli, I can find this reference for you if you want.
I can go it myself. Yeah, thank you.
Okay.
Yeah.
Okay. Good. Thanks for all these questions. Okay. Thank you very much for your attention. Okay, I think that indeed the host of the course, well, I mean, I don't know if the host is Chao Sen, I don't know if he's around, but I think we don't have a host. So essentially we can finish whenever we want, but if you don't have more questions, maybe it's a good point to stop the class. I mean, I'm going over 1 hour and a half, not only the first day, but the second day, but I hope it was useful for you somehow. I mean, I went very slow today, but I hope that it was understandable. At least you are ready for the problem sessions, that's for sure. Okay, guys, so see you next week, and well, have fun trying to solve all the list of the problems. Okay, now we will add more problems to the list, but you can already try to solve them. Okay. The one guys, the guys of the POW, do you want to say something?
Well, no, I was going to say that they are already prepared for the problem, since now they were already in this session resolving some of them in his
Exactly.
interventions.
Yeah, exactly. So we were indeed solving some of them. So the idea of today, indeed, my idea was to get to the blogging, but essentially I spent most of the time giving examples, but I think this was useful. I hope this was useful. In any case, I'll manage to see how I get how I get back in track with lesson 3, but I'll at least the Moser theorem, it's going to be quite easy to go over that. Okay, guys.
Okay.
See you soon.
Yeah.
Have
See
fun.
you.
I'll see you after. I mean, let's have lunch and then we talk. You and I, right? We have a meeting this afternoon. Okay, guys. See you soon. Bye. Bye.
人在日的话